The topic for this lecture is closure properties of regular languages. We shall see what are closure properties. Before that, let us recollect various mathematical representations that we learned for regular languages. If you remember, we learned about DFA representations, NFA representation, epsilon NFA representation, regular grammar representation and regular expression representation for regular languages. We also have proved that these are pairwise equivalent representations for regular languages, meaning given a representation, there exists an algorithm to convert it into any of the other four representations, and that is true for every pair of representations. Now, let us see what are closure properties for regular languages. We know that a language is a set of strings. So, it is a set. A closure property of regular languages is an operation which, when applied on regular languages, produces a regular language as output. A language is a set, so a property is a set operation which takes regular languages as input and produces a regular language as output. Let us look at an example. Union is a closure property for regular languages, since for all regular languages L1 and L2, we can prove that L1 union L2 is also a regular language. A language is a set, and a property is said to be a closure property of a regular language if that is an operation which takes regular languages as input and produces a regular language as output. Example closure property or operation that we saw is union. We can say that union is a closure property for regular languages, or equivalently we can say regular languages are closed under union, meaning if you take two regular languages and find the union of the two regular languages, then what you are obtaining is also a regular language. Now, what are the other commonly discussed closure properties? We can see that regular languages are also closed under Kleene iteration. That means if L is a regular language, then the star closure L star is also a regular language, and is closed under complementation, meaning if L is regular, then L complement is also regular. And regular languages are also closed under intersection, meaning if L1 and L2 are regular, then L1 intersection L2 is also regular. We can also prove that they are closed under string reversal, meaning if you look at a regular language, then the language which contains the reverses of strings in the original language, then that language will also be regular. We can look at each case. First, we will prove that regular languages are claused under union. We can have a claim which tells if L1 and L2 are regular languages, then L1 union L2 must be a regular language. We can have a proof given that L1 and L2 are regular. Then, without loss of generality, we can assume that there exists regular expressions R1 and R2 such that L1 is the language of R1 and L2 is the language of R2. That is a fair assumption because we know that every regular language can be represented in any of the 5 pairwise equivalent representations that we discussed. So, of course, you can find regular expressions for the languages L1 and L2. Then from the definition of regular expressions, we know that R1 plus R2 is a regular expression representing the language which is the union of the languages represented by R1 and R2. This is what we know from the definition of regular expressions, which means this is regular because there exists a regular expression for this language. And what is the union of L of R1 and L of R2? It is L1 union L2 because L1 is the language of R1 and L2 is the language of R2, and hence proved. We proved that whenever L1 and L2 are regular, then L1 union L2 is a regular language. So, regular languages are claused under union. Now, look at Kleene iteration or star closure. We can have this claim stating when L is a regular language, then the star closure of L is also regular. We have to have a proof. Given that L is regular, then here again assume without loss of generality that there exists a regular expression R such that L is the language of R. Then from the definition of regular expressions, we know that R star must be a regular expression representing the star closure of this language. That means the star closure of the language, which is L star, is regular because there exists a regular expression for that. And hence we proved that regular languages are claused under Kleene iteration or star closure. Moving on to the next closure property, we are going to state and prove that regular languages are closed under complementation. We can have this claim: if L is a regular language, then its complement, L complement, which is set of false strings set minus L, that is the set of all other strings. The language of the set of all other strings is the complement, which is also regular. Here we can have a constructive proof, and for that first see an example. This is a DFA, and can you identify what is the language represented by this DFA? You can see that if you came to the state R, then just before coming to that, the last simple read was a B and the second last simple must be an A. So, you reached into R means definitely you have processed AB as a string, and that is the language. You can verify that the language is the set of all strings X containing AB as a substring in it. Now, look at this DFA. A complement which I obtained by just flipping the status of the final states. All the final states, here only one, in the given DFA is made non-final, and all the non-final states here S and Q are made final. And here what we did is we made all the existing final states non-final and all the existing non-final states final. So previously if a string was accepted, then that must be rejected because that final state became a non-final. And now suppose previously some string was rejected, then that string must be accepted here because we made all non-final states final. So you can easily verify that here in this case, if the string is containing the string AB, then you will reject. You will come here and you will reject. And otherwise, in all other cases, you will accept. In fact, here you can generalize this to get constructive proof. We can say that if A is a DFA representing a language L, then we can obtain a DFA A complement from A, where the only change is the final states are toggled. Now, in the new machine, the final states will be all the non-final states of the given DFA. Then you can easily argue that suppose a string X is accepted by the given DFA. And why is it accepted? Because the processing of X ends in a final state. Now that final state became a non-final state and hence X will be rejected by the obtained DFA. So if X is accepted by the given DFA, the DFA A complement will reject it. Now you consider the other case. Suppose a string Y is rejected by the given DFA A. Then why it is rejected? Because the processing of the string Y ends in a non-final state. Then here in the obtained DFA A complement, that non-final state became a final state and hence Y will be accepted. So whenever a string is accepted by the given DFA, this string will be rejected by the complement DFA. And whenever a string is rejected by the given DFA, the complement DFA will accept it. So we can easily argue that what we obtained is a DFA accepting the complement of the language accepted by the given DFA, and hence we proved that regular languages are claused under complementation because we can obtain a DFA representing the complement of the language. And with this we are moving on to the next closure properties. We are going to prove that regular languages are claused under intersection. We can have this claim which tells if L1 and L2 are regular languages, then their intersection is also regular. We can use the closure properties that we already proved and De Morgan's law to prove it. Given that L1 and L2 are regular, then because regular languages are claused under complementation, we can say that L1 complement and L2 complement are regular because L1 and L2 are regular, and regular languages are claused under complementation. Now because L1 complement and L2 complement are known to be regular, their union must also be regular because we already proved that regular languages are claused under union. And here we have L1 complement and L2 complement as regular, so their union must also be regular. Now again apply the complementation property. If you take the complement of this language, what is it? The complement of this language. The complement of this language. This language is proved to be regular, So, the complement of that language is again regular, because regular languages are proved to be closed under complementation. Now, from De Morgan's law, we know that the complement of L1 complement union L2 complement is nothing but L1 intersection L2. That is De Morgan's law. And hence, we prove that regular languages are closed under intersection. Moving on to the last property that we are discussing in this lecture, we are going to argue that regular languages are closed under string reversal. We can state a claim: if L is a regular language, then L reverse, which is the set of all strings such that the reverse of that is in the original language. That is, if X is in the original language, then X reverse will be in the language L reverse. So, it is all the reversals of the string in the original language. Look at an illustrative example. This is an N of A given. Can you tell me what is the language represented? It is easy to see that the language is the set of all strings starting with A and ending with B over the alphabet set A. Now, just look at this N of A, which I obtained by reversing the direction of all the edges and making the start state final state and final state start state. That is what I did. So, what I did is I reversed the direction of all the edges and I changed start state to final state and final state to start state. And if there are multiple start states, you can change all of them to final states, and if there are multiple final states, you can change all of them to start states, because what you need is an N of A. Here you can easily observe that the language is the set of all strings starting with B and ending with A, which is the reverse of the language. And this is a generalizable procedure. We can use that to get a constructive proof. Given an N of A with a set of start state and a set of final states, one can construct an N of A reverse with the same set of states, new set of start states, new set of transitions and new set of final states, such that the language of A reverse is nothing but the reverse of the language represented by A, which is what we need. Now, we have to say what is S prime, what is delta prime and what is F prime. S prime is F, that is the set of all final states in the given N of A is going to become the set of all start states of the constructed N of A. Similarly, the set of all start state of the given N of A is going to become the set of all final states of the constructed N of A. And what is delta prime? Reversing the direction of edges. That means delta prime contains a transition from Q to P on A if delta contains a transition from P to Q on A. So, if there is a transition from A to B on A, then there is going to be a transition from B to A on small a. That is what we said. And now, once you have this construction, suppose there exists a path for X from a start state to a final state in the obtained N of A, then you can prove using mathematical induction on the length of X that there exists a path from the why you accepted in the new machine is there exists a path from start state to final state, and this is because there exists a path from the final state. So, because we reversed the directions of edges, if there exists a path for X from the start state to the final state in the constructed N of A, then that means there exists a path for X reverse from a start state to a final state in the original N of A. Maybe you are getting confused, but please think about it offline. You can prove that this is a correct construction. This is just an outline because I have not given the proof of correctness of this construction. Assuming that it can be done, we proved that regular languages are closed under string reversal. So today we have looked at closure properties of regular languages, which are operations on languages such that the result on acting on regular languages is again a regular language. And today we proved that regular languages are closed under union, intersection, complementation, string reversal, and Kleene iteration. And we can prove that regular languages are in fact closed under almost all the interesting set operations. If you want to look at more operations like set difference, you can try. How can you prove it? With this, we are finishing this lecture. Thank you.